Hi everybody, we're going to be taking a look at page 105, problem number 87, which gave a lot of people fits. One of the problems with 87 is that part A does not correspond to the diagram. So we're going to take a look at this problem and see if we can knock it out. What we have here in part A are two separate blocks that are not yet connected by the string. The connection with the string doesn't happen until you get to part B. And just for the fun of it, they gave us two different coefficients of friction for the two different blocks. In real life, that would happen if the blocks are made out of different materials. We have a 30-degree angle here. And now they ask, what is the acceleration of each block? And so we're going to need to treat each block separately. So here's block 1, and we know enough to know that we're going to have a component of gravity that is mg sine 30 here, and mg cosine 30 here, and a normal force Fn, and a frictional force F equals mu times normal. Now in this particular case, we can come up with numbers for all of these. Mg sine 30 degrees is simply going to be 1 kilogram times 10 times 0.5, which is 5 newtons. And this turns out to be 8.7 newtons. And because the sum of forces in the perpendicular direction is going to be 0, and there are only two forces, the component of gravity perpendicular and the normal force, immediately we have Fn is equal to 8.7 newtons also. And finally, the force of friction, F is equal to mu times the normal, which is going to be 0.87 newtons here. And so we have a pretty simple calculation in the parallel direction for the 1 kilogram block. We have sum of forces is equal to 5 newtons minus 0.87 newtons is equal to mass times acceleration, or 1 kilogram times acceleration. And that gives us 4.13 newtons equals A times 1 kilogram, and the acceleration is 4.13 meters per second squared. So that's the first block. What changes when I go over to block number 2? Well, all of the components of gravity are going to be simply twice as large. So I can immediately write this as 10 newtons, and I can immediately write this one as twice 8.7, or 17.4 newtons. And that means that the normal force also will be 17.4 newtons. The frictional force is tricky because of the differing mu. The frictional force is going to be mu times the normal, which is going to be 0.2 times 17.4 newtons, or 3.44 newtons. And so for our 2 kilogram block, we have sum of forces in the parallel direction is equal to 10 minus 3.44 newtons equals 2A, or 6.56 newtons equals 2A, or A is equal to 3.28 meters per second squared. Now what's interesting about this is that our two blocks have two different accelerations, and the one on the bottom is accelerating at a lower rate. So that means that eventually the top block is going to run into the bottom block. So there it is for part A. Two different blocks, not attached, and so you have two different accelerations. Let's take a look now at part B. In part B, you have the same two blocks. Now they're attached by a, quote, taut string. And you let them go, and what happens? This part right here is exceedingly tricky. And the reason that it's tricky is that because the top block is accelerating faster than the bottom block, the string is actually not going to remain taut at all. As soon as you let go, the top block is going to race down towards the bottom block, and the string is going to go slack. And if the string goes slack, then it might as well not be there. And so I conclude that the answers should be exactly the same as for the previous problem. For the 1 kilogram block, we should get an acceleration of 4.13, and for the 2 kilogram block, we should get an acceleration of 3.28. And the reason is that as soon as we let the blocks go, then there is no tension in the rope, and the free body diagrams look exactly the same as they did for part A. Very interesting problem. We have a saying in physics, you can't push a string, and that's what this part is trying to teach. That because the one is accelerating faster, it's trying to push that string, and there will be no forcing. We can do C on the same page here. Part C, we have the same system, but now we're going to reverse the two blocks like this. Now the 1 kilogram would be dragging the 2 kilogram block, and the result is that the two of them, the string is going to remain taut, and the two of them are going to fall as a single system. Let's analyze it as a single system. We're going to have the 1 and the 2 attached together so that the whole thing is one object. There'll be a normal force here and a normal force here. And we already have all of the components that we need. We know from the previous problem that the effective gravity is going to be 5 newtons here and another 10 newtons here. And we'll have a we'll have a component of gravity of 8.7 newtons here and twice that, or 17.4 newtons here. And the normal forces will correspond. If the mu had been the same for both blocks, I would have just treated this as one 3 kilogram object. But because I have two different mu's here, I have to have two different frictional forces. And we computed those on the previous page. This was 3.44, and this was 0.87 newtons worth of friction. And so now, here comes the single system analysis. We're going to treat the whole thing as one single object. We're going to add up all of the forces in the parallel direction. That's going to be 5 newtons pulling down the plane, plus 10 newtons, minus 3.44 newtons of friction, minus another 0.87 newtons of friction. And all of that is equal to 3 kilograms, the combined mass of the system, times the acceleration. And when you punch the numbers in, then you get a total of 10.69 newtons equals 3a, and the acceleration of the system is 3.56 meters per second squared. You can see that that acceleration is somewhere between the two accelerations that we got for blocks 1 and 2 on their own. and that's a reasonable conclusion to come to. So I hope this helps. There was a thought in the 6th period class that perhaps the back of the book answer was incorrect, but actually it was correct all along. And the reason for that is that the string, even though the problem says in part B that the string begins taut, it does not remain taut forever. Hope this helps.